Hey, wizards. So the same problem again. This time, though, we're going to take this problem and look at it from a hypothesis test approach. So again, we're still going to answer the same question: is can she conclude that more than 60% of employees at the company are satisfied with their jobs? But we're going to approach this problem from the point of view of the population. So we're going to kind of believe in the population, but we're going to look out at the sample and we're going to see how odd or unusual our sample might be if the population is actually true. So again, we check our conditions. We've already checked two of them. We know that they were randomly selected because it says so right here in this line. And we are going to assume that the sample is not too big. Our sample of 100, certainly there must be more than 1,000 working adults in the United States. The key difference is the big enough condition. The big enough condition is the key difference. In a hypothesis test, we use the null proportion, which is typically denoted as p with a sub-zero, like the null hypothesis. So that is actually equal to 0.6, and I get that from up here in a couple of different places. And so assuming that this is true, that my population proportion is 0.6, and I take a sample of 100, I would expect to see 60 people who are satisfied with their job and 40 people who are not satisfied with their job. And both of those are greater than 10. So again, what I'm looking at is I'm predicting what I would expect to see out of a sample of size 100. Whereas in a confidence interval before, I actually had my sample and I used what was in my sample. So the sample size of 100 is large enough. So the null hypothesis states that my population proportion is 0.6, or in words, the proportion of employees satisfied with their job is the same as the population proportion, and that is 0.6. My alternate hypothesis, coming from what I believe to be my wanting to conclude more than 60% of employees at the company are satisfied, would be P is greater than 0.6. The proportion of employees who are satisfied with their jobs is greater than the population proportion. And so I'm looking for evidence that leads me to believe that maybe the proportion is greater than 0.6, but I really won't know until I continue on. So write the model you are using and don't multiply anything out. So our normal model is based on the null hypothesis. When you're doing a hypothesis test, you believe in the population. So our population is what we use. So this is my null hypothesis. So is that, and that's the Q that goes with it. So I build my model using what I know to be true about the population, or what I am assuming to be true. Part E, is this a lower tail test or an upper tail test or a two-tailed test? Well, you get this answer from your alternate hypothesis. So my alternate hypothesis said that P is greater than 0.6. So that is an upper tailed, and it's a one-tail test. If it was the other direction, P is less than 0.6, that would be a lower tail. And if it was a not equal to, if it was P not equal to 0.6, that would make this a two-tailed test. But as it is, we have an upper-tailed, one-tailed test. So the p-value. Here's my model. My model is based on the null proportion, p0. Here's my p-hat. So my sample said that 64% of my sample of 100 said they were satisfied. So what I'm interested in is how likely is it, if the null hypothesis is true, to see a sample proportion of 0.64 or greater. And using normal CDF on my calculator, I come out with a probability of 0.207, and that, recall, is my p-value. So my decision, since my p-value of 0.207 is larger than any reasonable alpha level, and by reasonable alpha level, typically it's either 10% or 5% or 1%. I fail to reject the null hypothesis. Remember, we either reject or we do not reject. That's how we word it. We reject the null hypothesis or do not reject. This is for large p-values. And our p-value is large, so we do not reject the null hypothesis, or we fail to reject. Describe what the p-value means in context. Well, the p-value is a conditional probability. What it says is the probability that my p-hat would be greater than or equal to 0.64, given that the population proportion is actually 0.6. So given the null hypothesis is true, in other words, given that p is equal to 0.6, how likely is it to see a p-hat, my p-hat was 0.64, as large or larger than 0.64? And that probability, again, is 0.207, which is large, larger than any reasonable alpha level. Can she conclude that more than 60% of employees at the company are satisfied with their job? She cannot. We don't have evidence that they do. So we don't have evidence, so she can't conclude that. I'm not saying that they're not. It could very well be the case that more than 60% of employees at the company are satisfied with their job, but we don't have evidence to suggest that, so she cannot conclude that. So that was the hypothesis test approach to the same problem again. So you've done it in a confidence interval approach, and now we've done it as a hypothesis test approach. And hopefully you should be fluent in both of those as we go throughout the next couple of weeks. So that's that, wizards. I hope this has been helpful.